Do that. And that. All right. So about, I don't know, maybe back in probably like 2000, this might have been 2009, 2010-ish. Uh, the bookstore kept going up. I think I might have told you guys this already. The bookstore kept jacking the prices up on the textbook. So back in 2004, I got rid of the textbook and just put everything on PowerPoint. We kept the lab manual, which was reasonably priced, but for whatever reason, it kept going up on that. So a couple years ago, I asked the students if they would want me to order the book and get it through the bookstore and have the additional profit tacked on that UC would tack on, or did you want to just get it online off Amazon? You find it yourself. And they decided they go and just order it offline. So since then, I haven't been ordering the updated lab manuals for this class at the bookstore. Students have just kind of been finding the lab manual on their own on Amazon or whatever resource you use online. So what I'm showing you here is the cover to the lab manual you'll need. Now, you don't need it right now, probably in about 2 weeks, I would say. So I want to show you what the cover looks like. And for two reasons. Number one, to give you enough time to get it, of course. Number two, the lab manual, there's a lab manual, there's a textbook, and there's something called an activities manual. And unfortunately, they all look exactly alike. So in the past, I've had students buy one book trying to buy the lab manual, but they actually bought either the activities manual or the textbook. So when you order this, you want to be careful that you actually look at it because they look exactly alike. You want to make sure you have this on there. It says lab manual. It says Logix Pro PLC lab manual for use with programmable logic controls. It's got to say lab manual on it. I think the textbook doesn't have anything at the top. I think the activity said activities manual at the very top, but this one says lab manual. So make sure when you order your lab manual, and I did on the back of here, you can blow that up. You'll see the ISBN number, so to make sure you're getting the right book. So again, you don't need this right now, but I think around week 6, we'll switch over to the new schedule, and then I'll start assigning lab work out of this book. So you want to make sure you go ahead and get it. I'm just showing it to you now so that you have enough time to order it. I did put a link on our homepage. If you go to the homepage, scroll down towards the bottom, right above my name, you'll see a link. One says past videos. You can click on that and see the past lectures we've had so far. But right below that, you'll see the link to this cover for the lab manual. The other thing I want to mention about the lab manual is I think you can use the 5th. You can use this is the 4th. You can use the 4th, 5th, or 3rd edition. I think any of those will work. I don't think I have a 3rd edition, and I don't think much has changed from the 3rd to the 4th. I haven't looked at the 5th, but I do think some students might have used the 5th in a previous semester. So any of those is okay. I think you'll save a little money by getting the 3rd or 4th edition if you can find it. But somebody sent a text out. I don't know if it might be kind of hard to find. I don't know. Just let me know if there's any issues trying to find that. And I think they're out there. But what I was going to say is, when they actually sold this book in the bookstore, they had the lab manuals with the CD and without the CD. So if you can, when you order it with the CD, and on the CD is your PLC simulation software. It's called Logix Pro. If you can do that, then you won't have to pay the additional cost for the software. If you get a lab manual without the software, then there is a link that you can go to, and I'll give you that link a little bit later on. You can go to and you can download the software. It's like $35 or $40, but you can kill 2 birds with 1 stone. If you can find the lab manual and it says with CD, then you can go ahead and get the lab manual and the CD, and you don't have to pay that extra money for the simulation software. So I'm trying to save you guys money. I mean, I know you know the cost of books nowadays, and I think you can still get all this online. I almost forgot to turn. Yeah, so go ahead, guys. Somebody mentioned the attendance. Let me switch off of this and go to the camera. Go ahead and send your attendance in. Go ahead and do that right now. Send me your text 494-6162. Logic control. Make sure you put your first and last name. And what else I want to say? So I looked at the homeworks. I think homework 2 you turned in. You guys did an excellent job on homework 2. I think everybody got an A on that. So good work. There were 2 people. I'm not sure why, but there were 2 people that I don't know if you missed the deadline for whatever reason. I did have 2 people that didn't get a chance to turn it in. So that link probably disappeared because I think it was set to expire on Sunday night. But if you submitted it, I think I checked it. You guys did a good job on it, so keep up the good work. Now, unfortunately, I have an appointment right after class. I did have a student that wanted to ask questions about the quiz, so I'm assuming that if I have one student that has questions, I might have others that might want to ask some questions. But what I'm going to do is either send me a text and I'll open up a link and we can talk tomorrow, or after class on Wednesday, I'll stick around, and if you can remember the questions, we can talk about the quiz if you have questions with it. If you don't, I can probably open it up and we can go through it. I'll be more than happy to do that. But today I got to leave, probably cut class short a little bit, and I got a meeting off campus I have to attend to. I think that's it. So make sure you text me. And today what I want to do is I do have a PowerPoint for today, but I think I want to just kind of talk about this stuff on the board, and then I'll go through the PowerPoint real quick to make sure we covered everything. So what I want to talk about today is oh, wait a minute. You know what? This is the one. Can somebody try to talk to me through your microphone? This was the one I couldn't hear you. Somebody say something.
Can you hear me?
I'm still having issues hearing you guys. I know you can hear me, but I'm not able to hear you. I don't know why. Okay, let me see. Let me just, people are taking, okay, Will, Will, try to open, you have a microphone, Will? Try to open up your mic and say something. Let me go to my list.
I don't think you can hear us.
I guess.
I don't think so.
Ethan is trying to talk. Okay. I'm still having issues hearing you guys. I hate that. I don't know what the heck it is. I don't want to waste time doing this, but it's just if you have questions, it's a little harder for me to. All right, I'm not gonna, I'll try to watch my screen. It's a little hard because the screen is on one side of the room and okay. I don't know what the heck is going on with this. I'll see what, I'll see if I can get this looked at by next time. I know I said that before. And Ethan, thank you for opening up there's a real person out there. Glad he opened up his camera. So today, I want to talk about machine language. Machine language. Machine language. And you know that digital devices communicate using ones and zeros. And the name of that is binary. But actually, this binary is what we call a number system. So all digital devices communicate using zeros and ones. That's called machine language. But there's really 2 types of data or information. You can have numbers, and you can have codes. So I can have digital numbers, or I can have digital codes. And what I want to talk about today is the first one, digital numbers. So this is all part of machine language. just remember what we said before in another lecture is we talk about machines communicating using zeros and ones, but really all an electrical device can understand is the presence or absence of a voltage or current. That's it. So we're really dealing with the presence or absence of, and we use these numbers, 5 volts to represent a binary 1, 0 volts to represent a binary 0, and these are ideal values. So I just want to store ones and zeros. The presence of 5 volts is the 1. The absence of the 5 volts, 0 volts is a binary 0. And so there's a lot of ways to do it. I don't want to go into the technology, but there's a lot of ways I can store up capacitors, some of the 5 volts, some of the 0 volts, and I can store information that way. Usually it's done electronically in something called a register. And in the register, these things called flip-flops, and flip-flops just hold voltage or not hold voltage. So there's a lot of ways to do it. But 5 volts is a 1, 0 volts is a binary 0. That's if I want to store the zeros and ones. If I want to move it around, then I got to introduce the idea of a digital waveform. So we talked about a positive going pulse. It looks like that, or a negative going pulse looks like that. So if I'm holding these zeros and ones in memory, well, 5 volts is a 1, 0 volts is a 0. If I want to move it, let's say from memory to the microprocessor, from the microprocessor to memory, or from the memory to the printer, now I'm talking about data transfer, and I gotta move a 1 like this, and I gotta move a 0 like this. I put these together, and I get what's called a pulse train or digital waveform. So we kind of talked about all of that. Today I want to drill down into binary to binary number system. And to get you to understand what we mean by a number system, let's look at our own number system. So our number system, the ones that we use as humans, is based on 10. We use a base 10 number system because we have 10 digits. I have 10 fingers, 10 toes. So back in the day when we were probably, I don't know if we go back to cavemen and women, but we were a hunting and gathering society. Maybe we had to count sheep or cattle or something like that. So I can use my fingers, I can use my toes, it's a base 10 number system for biological reasons. Now, how does our number system work? So back in, I don't know, maybe 2nd or 3rd grade, you learned about place value. So you had something like this. You learned that this is the ones place, this is the tens place, that's the hundreds place, this is the thousands place. So you learn something called place value. At least when I was in school, that's what we called it. We called it place value. So given place value, you know that we have these digits in our number systems. We have 10 symbols we use for digits or for numbers. And they are 0 through 9, right? 0 through 9. And I only have those 10, so what I'm doing, I want to count, like I can count, like if I start counting, now normally in digital, we start counting with 0, but for now I'm going to count with 1. What I can do is I can go 1, 2, 3, 4, 5, 6, 7, 8, 9. So I can count really from 0 to 9, put a 0 there. So I can count 0 to 9, and I ran out of digits. So how do we fix that? When I run out of digits, I just start doubling them up. I'll say, all right, I'm going to go 1 again, and I'm going to start this count over here again. 1, 0, 1, 1, 1, 2, 1, 3, and we keep going all the way up to 99. When I get to 99, I ran out of digits. I keep adding a place, and we get this idea of place value. So if I do something like this, let's say I put 1, 0, 2, 4 there. So what exactly does that mean? Well, that means that this place right here is worth this amount. This place right here is worth this amount. This place is worth this amount. This place is worth this amount. But the number, the digit we put there, tells you how many of these things we have. So what I'm saying is, this says that we got one of these, so it's going to be one. Let me just do it this way. It's going to be 1,000 times 1. I got none of these, so it's going to be 100 times 0. I got 2 of these, so it's going to be 10 times 2. And I got 4 of these. It's going to be 1 times 4. So over here I get 1,000. Here I get a 0. Here I'll get a 20. And here I'll get a 4. And if I add those up, I get 1024. So that's the meaning of this. Now, in digital, when we deal with digital, what you call place value, we're going to call that a weight. So this place right here has a weight of 1,000. This has a weight of 100. This has a weight of 10s, weight of 9, and so forth. Well, if you want to, instead of writing this like that, you can put it in, you can write it as an exponent. And there's a reason why you want to do that, but let me show you what I'm saying. You can write this like this. You can write this like 10 to the 0. 10 to the 0 is a 1. This is 10 to the first. 10 to the first is 10. This is 10 to the second. 10 to the second is 100. This is 10 to the third. 10 to the third is 1,000. So instead of writing it out like that, I can write it out like this. This is 10 to the third, 10 to the second, 10 to the first, 10 to the 0. Now, why would you want to do that? Well, if you do that, this will be a little bit more clear when I get to binary, but if you do that, then when we count, we can just use the powers here, the exponents, as the position number. So in other words, the 4 is in the 0 position, the 2 is in the first or the 1 position, 0 is in the second position, and 1 is in the third position, position 3, I should say, not the third position. So if I write it as a power, then I can the exponent of the 10 becomes the position of the digit that we're referring to. The other thing is this, is that if you write it like this, then I can write it like in general like that, then this right here is called the base of the number system. Well, if you take the base of the number system minus 1, let me put this over here. If you take the base of any number system minus 1, it gives you the value of the highest digit. That's what I'm saying is, if we have a base 10 number system, we got a base 10 number system. If I take the 10 minus 1, it gives me a 9. That means the symbol, the highest symbol I can use in this number system is 9, and you know we do that. We go 0 through 9, and I got to start repeating the digits like I showed you before. So we're all familiar with the base 10 number system. Well, here's the cool thing. Any number system works like this. And what do I mean by any number system is, well, we as humans, we use a base 10 number system because we have 10 digits, but there are actually other number systems that we're going to explore and talk about. Matter of fact, if you want to, after what I show you today, you can make up your own number system if you want to, any number system. So I can write this more generally like this. That base, we always call that B for base, to the end. This is any old number system. This will be the base. We just talked about a base 10. As humans, we use a base 10. Well, computers, their fingers are really switches, and where we can count to 10, a switch can either be on or off. So think of a computer as having just 2 fingers. So it can only count 0 and then 1. So we can have a base 2, we can have a base 8, any base you want. And they all act like this one right here, if you know what you're doing. So the base will tell you the number of symbols you have. The base minus 1 tells you the value of the highest symbol. So a base 10 number systems, we got 10 symbols, and the base minus 1 is 9. So 0 through 9 are the 10 symbols I'm referring to. Well, that works with any number system, including a base 2 number system. So let's look at what would a base 2 number system look like, and let's compare it to what we already know about our number system. So base 2 would be this, 2 to the n. And remember, this tells us how many symbols we have. So in this base 2 number system, I can only have 2 symbols. And if I take the base minus 1, it tells me the value of the highest symbol. So 2 minus 1 is a 1. So in the 2 number system, the only digits I can use is I can use a 0 and I can use a 1. And if I run out, I got to do just like we do in our number system, base 10. When I go 0 through 9, when I run out, I start to repeat. I go 1 0, 1 1, 1 2, 1 3. We do exactly the same thing in every number system. So base 2 number system, as you already know, is called binary. And binary is the language of machines, the language of any digital device. And so if we look at the binary number system, and we think about place value, now remember in binary, we don't call it place value, we call it weight. So each place has a weight. And so let's say I have this. Well, to get the weight, you do exactly like we did in base 10. This would be the base to the 0 to get the weight of this place. The weight of this is a 1. This would be 10 to the first to get that second weight. Well, that's a 10. So this has a weight of 10. 10 to the second, well, that's 100. So this has and so forth. You do exactly the same thing, but we're dealing with base 2. So right here, this is 2 to the 0, and this is the 0 position. This is 2 to the first. That's position number 1. This is 2 to the third, and this is 2 to the 4. You can just keep going. 2 to the 5th, 6th, 7th, as big as you want. We'll stop right here at 4. So that means that 2 to the 0 is a 1, so this has a weight of 1. 2 to the first is 2, so this has a weight of 2. 2 to the third is not 6, it's 8, so this has a weight of 8. 2 to the 4th, 16, so that has a weight of 16. 2 to the 5th is 32, 64, 128. You can keep going. Now remember, unlike base 10, where we can use 0 through 9, we can use all those symbols. In binary, there's only 2. You can use a 0 or 1. So all I'm allowed to put right here is 0 and 1. Now, oh, you know what? No, you can't. I was going to say, how come I made a mistake and nobody said anything? Because you can't talk to me. I forgot the 2. I got to get that fixed because I don't like not being able to talk to you guys. So this is 2 to the 0, 2 to the first, 2 to the second, 2 to the third. And so this would have a weight of 1. This has a weight of 2. This has a weight of 4. This has a weight of 8. And then 16, just like I said before. So they call this, just kind of a shorthand, they call this, if you put this in a box, they call this 8421 code as a shorthand. But the point I was trying to make before I caught my mistake, you can't, the only thing you can put here is a 0 or 1. So if I get rid of these, since I now know the weights here, this is an 8, 4, 2, 1. You can see as you go this way, they double. So I can go 16, 32, 64, 128, 256. I keep going. Just double this as you go out more. So let's say in our number system, 12, right? If I put that into your microprocessor in your cell phone in your computer, it doesn't know anything about the number 12. What it will put into the register of your digital device is going to put a 1, 1, 0, 0. And just like over here, I can take this thing times the weight to see what the value is. I can do exactly the same thing over here. So what does this mean? It means that I got one of these, so I got an 8. I got one of these, so I got a 4. I don't have any of those. I don't have any of those. So I got a 12. So I would say 1, 1, 0, 0 in binary is equal to a 12 in our number system. We got a problem though. We got a problem, and the problem is this. Say you walked out of the room, and I put this on the board. Then you walk back in and you look at that and you say, what is that? Well, you probably think to yourself, well, that's a number 11. But we don't know that now that we have more than one number system. This either is a number 11 in our number system, or it is it'll be a 2 and a 1. So if this is our number system, that's number 11. But if this is binary, then that's a 3. How do I know? Well, the way we're gonna know is that from now on, from today on, anytime you write a number down, you have to put a little subscript to say what the base is. So like right here, if that's a binary number, I'm going to put a little 2 there. If that's a decimal number, I'm going to put a 10 there like that. You got to do that because we're going to talk about, we got our number system, base 10, we got binary, and then there's 2 more number systems we're going to deal with. So we got to know which number system we're in, and to do that, you're going to use a little subscript. If it's a base 2 number system, put the base right there. If it's a base 10 number system, put the base right there. If it's some other number system, whatever the base is, you just put it there as a subscript. So you got to understand the sequence. And what I said before, when you type in, say on your cell phone, you're going to use your calculator on your cell phone, you type in 1, 2. Not the digit 1, but you want the number 12. You type in this number 12, base 10, and what's going to happen is when you hit enter or add or whatever it is you're doing, inside those registers, there's going to be one of these because we need an 8 to make a 12. One of these because we need a 4 to make a 12. We don't need a 2. We don't need a 1. So 12 in our number system to the machine, to the computer, looks like a 1, 1, 0, 0, and you got to put the little base there for base 2. Now the neat thing about this 8421 code you can make this little box 8421, and then you can convert any number to you can convert any binary number to decimal quickly, but if using that box. And just remember, as you go on, you just double. This is 16, 32. As you go to the left, it just doubles. So if I threw at you on the quiz, I say, all right, what is this? So I got a 1, 0, 0. To the computer, it looks like what to us? Well, I got an 8. I don't have a 4. I don't have a 2, and I got a 1. So a 1, 0, I don't know if you guys can see that. So a 1, 0, 0, 1 base 2 to the computer is this, but what we mean in our number system, it's a 9. So using this, you got a real quick, handy way of converting over, given a binary number, converting it to decimal, or going the other way. You should be able to do that. Now, these positions, and we'll just do 4 positions. So these positions in binary, the leftmost bit position, the leftmost bit position is called your MSB. That stands for most significant bit. Most significant bit. This right here is the most, this is 1,000. So if this was money and you were going to lose it, you'd rather lose this part of it. You'd rather lose $4 than to lose that part of it. You don't want to lose 1,000. This is more significant. It was the same way over here in machine language. The leftmost bit is our most significant bit. It carries the higher weight. And then this one right here is our least significant bit. but you'll see the term MSB and LSB. I want to make sure that you are clear on what those are. Now let me pause for a second and see, because I've been looking to see if you guys have been sending them. Anybody have any questions on anything so far? And I got to get this, I really got to get this audio fixed because that drives me crazy. Okay, so the other thing I want to show you, and then we'll go to the PowerPoint. Yeah, I got time. We'll go to the PowerPoint. There's kind of a, if you have like a bigger number and you want to convert it from base 10 to a binary number, they do something called a divide by 2 method. A divide by 2 method. Let me just show you what that looks like. This is all in the PowerPoint, so you'll have an example of this. And I think on your homework, you got to do this for me, but it's all in the PowerPoint. So you can do it this way. I call this a sum of weights method. You just sum up the weights to get your decimal value, or you can do it this way, a divide by 2 method. So let me see, I think in the video, in the PowerPoint, I think I use, we can use whatever, but I think I use 47. So I got a 47 base 10. And I want to convert that to binary. And I could just make a whole bunch of cells here and do my 8421. I can do that. But another way to do it is you just keep dividing the number by 2, and whatever your remainder is, you get these binary digits. The remainder gives you the binary digit. You just got to remember that the first remainder you get is your LSB. Well, let me show you what I'm saying. It'll make sense. So if I want to convert this to binary, to machine language, but I don't want to use my 8421 code, I can say, all right, I'm going to divide this by 2. So divide that by 2. That's a 2. That's a 3. And if I multiply, that's a 46, right? And then when I do my subtraction, I get a 1. That 1, your remainder, that 1 right there is your binary digit, but you got to remember it's your LSB. That's your LSB. So if I want to write just to keep track of it, we'll keep the number over here. So I got a 1. That's my LSB. And then what you do is you just, whatever this is, you just keep dividing that number down by 2. So 47 divided by 2, 23, I have 1 remainder. That was my binary value, that 1. Then I'm going to take 23 and do the same thing. So I'll take 23, divide that by 2. I get a 1 there. I get a 1 there. 11 times 2 is 22. I got another 1. So my next binary bit is a 1. So over here, remember that first one was my LSB. So then I got a 1. And then I'm just going to keep doing that. I'm going to take this one, and I'm going to divide that one. So I got, I guess I'll do it over here. I got 11. I'm going to divide that by 2. 2 goes into 11 5 times. That gives me a 10. I got another 1 as a remainder. So I got another 1. And then I'm going to take this and just keep dividing that down by 2. So I got 5, I'll divide that by 2, gives me a 2, 4, I got another 1, I got to add another 1 to it, and then I'm going to take the 2, so I got 2, divide that by 2, and that goes 1 time, 1 times 2 is a 2, I don't have a remainder there, I got a remainder of 0, so I got a 0 there. Now, a lot of times students stop right there when they get to a remainder of 0, but you got to keep going. You got to go one more time. So I'm going to take this one, and I'm going to divide that. And I'm going to think out loud. Here's what you say to yourself. I got a 1. I don't know if you guys can see in the camera over there. So I'm going to take this 1. I got a 1. I'm going to divide that 1 by 2. Well, 2 won't go in the 1. So I'm going to put that as a 0. 0 times 2 is a 0, and 1 take away 0 is a 1. So then this one right here, that one right there, that's my most significant bit. That's my MSB. Okay, so I don't know if, let me see, is there a way for me to share my desktop with you guys? Hold on a second. I'm not really good with this share. Okay. Let me see what happens if I do. I want to show you, okay, I'm going to click off of this. Let me see what happens when I do this. Hopefully I don't screw this up. I want to try to share my screen. And then I want to share the window. No, I want to share the screen. But I really want to share the calculator. Let me see if I can share the calculator. Can you guys see the calculator? You got to text me and let me know if you can see that. No, okay. All right. All right, well, let me go back. Wait a minute, let me try something again. Uh-oh. Okay, it's not letting me. I don't know what I'm doing. I was all right, well, let me go back. Can you see me again? Can you see the board? I really wish I could. Oh, you know what? I know what I might be able to do. Let me try it this way. I don't know what this will do. Let me see if I can project it. Let's see what happens. I'm not seeing anything now. Oh, because I have on. Can you guys see that? Can you see yourself? Can you guys see that or not? Ethan, okay, so let me show you this calculator. All right, so I'm going to the calculator app, and then, well, my camera shadows right there. Let me see if I can make this a little better for you. I don't know how to move this. Okay, so what I'm going to do is at the bottom right screen, you can share your screen. Okay, well, I'll have to learn that later, but where my calculator disappeared? Oh, it's back here. Okay, so you guys can see that, right? So I'm going to go right here, and if you go to Programmer, and you can use this when you're doing your homework. I don't care, but I mean to check your homework. But I was on Standard. I was on that. If you go to Programmer, then you'll notice you got this list over here. Well, this DC stands for decimal, and right here stands for BIN. That's binary. And so you can click one of those. So right now I click this one. I click binary, and I don't know if you can see it or not, but the only thing you can see down here is a 1 or a 0, right? So if I type in, well, before we did a number 12. Number 12 in binary was a 1, 1, 0, 0. So that's the binary number. Now if I come over here and I click decimal, it's 12, or actually it shows it right here. So remember we did a 9 before? So if I type in a 1, 0, 0, 1, I don't know what I just did. Let me clear it. I think I typed in too much. So if I type in 1, 0, 0, 1, oh, I'm back to that. Let me try it again. 1, 0, 0, 1. So and you can see in binary that 1, 0, 0, 1 and base 10 is a 9. So the point I just wanted to show you that you can use this little app to check your homework. I think in your homework you got to do some conversions or something for me. So you can use that to check it if you want to. Good to do a lot of this by hand so you learn it, but you can check it if you want to that way. So so anybody have any questions? I want to go to the PowerPoint. I'm going to go through it kind of quickly because I pretty much went over everything, but there are a few things we have to talk about in the PowerPoint on signed numbers. So anybody have any questions before I switch over to the PowerPoint? It's like 100 degrees in this room. The air doesn't work. The sound's not working. All right. Okay, so binary number system. So why do we want to look at number systems? Well, the main reason is depending on what we're doing, we understand that digital devices only deal with zeros and ones. So we got to understand machine language or binary. But also we use other number systems to conveniently display addresses or data or codes. But just remember, no matter what number system we're in, when that number system goes into a digital device, it gets converted to binary. It's converted to ones and zeros. So this makes working with digital devices a lot easier to understand what they're doing. We talked about the general rules for any old number system. I can have, this is right here, it's called the base, but it's also, they use this term in math, the radix. So radix or base. And then down here, what we said is the base or the radix tells you the total number of symbols in any number system. So a base 10 number system is going to have 10 symbols. If I take the base minus 1, 10 minus 1 is 9, but the base minus 1 gives you the highest number and the highest digit in any number system. And so in the base 10 number system, you're familiar with that. Each place has a weight or position. If you write it like this, then that exponent becomes the position number. So each place has a place value or a weight. Of course, we're interested in the binary number system, so we're going to use a base 2 because we got to represent the state of a switch, and the switch can be either in one position or another. So base 2 number system makes sense to use in digital. And so the base minus 1, 2 minus 1 is a 1. So the highest symbol we can use in binary is a 1. And since I have a base 2 number system, that means there's going to be 2 symbols that I use, and they, of course, are 0 and 1. We mentioned, though, that, remember, what we're really dealing with is not zeros and ones. That's just an abstraction. What we're really dealing with is the presence or absence of a voltage, either 5 volts or 0 volts to represent a 1 or a 0 respectively, or a positive going pulse or negative going pulse to represent a 1 or 0 that we might want to move from one place to another. Now here are some terms. So if you printed out your PowerPoint, make sure, and you print it out 3 to a page and with the note pages, you want to mark this slide. You want to make sure that everything I have here in blue, you understand what is meant by that. So I think this we talked about before. We know a bit is a 1 or a 0. It's the smallest piece of binary information you can have. A bit is a 1 or a 0. A register is an actual hardware device that you can go through. You can go to a store, you can buy a shift register or a register, and the job of that device is to store ones and zeros. So if you were designing digital systems from scratch, you could go get a register, and you can purchase a register of a certain size, and you can store binary data in that register. So understand that a register is a physical device. A word is just a virtual construct. A byte, a bit is a 1 or a 0. We learned in the last class that a byte is 8 bits. But a word is machine dependent. A word depends on, you can have any word size you want as long as there's some power of 2. So I can have a word size of 1, word size of 2, 4, 8, 16, 32, and so forth. for the purposes of this class, even though we know that a register is hardware and a word only exists in memory, it's basically software. For the purposes of this class, we can consider a register and a word to be the same thing, just to keep things simple. Now, it's important to know your word size, because your word size is going to, for any PLC, the word size is going to dictate how many screw terminals you can connect physical switches to. So if I have an input module, and that input module has 16 screw terminals, I would label them 0 through 15, because in digital, we don't begin counting with 1, we begin counting with 0. So 0 through 15, but I have to have a place in memory to store whether that switch connected to that screw terminal was open or closed. It's going to store an open switch in the register as a 0. It's going to store a closed switch in that register as a 1. And you can map the screw terminals to the positions or to the cells of a register by using something called an address. We'll say more about that later. So for us in here, a word and a register are the same size, and our register sizes are going to tell us how many connection points we have on our input module, our output module, our hardware. So it mentions here that 8 and 16-bit words are most common. So 16 bits are probably the most common. Now, when we talk about words, for us, a word, even though we know a word is machine dependent, your simulation software has 16 connection points labeled 0 through 15. So that means for us in this class, a word is going to be 16 bits. A word in this class is 16 bits. So on the exam or quiz, if I say, what's the word size? How big is a word? You can either say it's 16 bits, or you can say it's a word is machine dependent, but for us in this class, it's 16 bits. We're going to use 16. And if we use 16, then the anatomy of a word looks like this. I have my most significant bit, which we talked about. That's always your leftmost bit. And I have my least significant bit. But I also have my lower byte. Here's my lower byte. This is my first 0 through 7. And here's my upper bytes, 8 through 15. So I can talk about an upper byte, and I can talk about a lower byte. I can talk about LSB, and I can talk about MSB. So that's important to understand, because sometimes when we move information around, we split the byte up. We might send the upper byte first and then the lower byte second, and reconstruct it when we get it to wherever we want in our system. So upper and lower byte. Now, this next slide is important that you know how to do this calculation. Now, don't be tricked, and I'm not trying to trick anybody, but remember kilo, kilobit, kilobyte, kilo with a capital B is a byte, lowercase b is a bit. So kilobyte and kilobit, that word kilo, the prefix kilo depends on what we're talking about. If we're talking about a kilobit, then kilo means 1,000. If we're talking about a kilobyte, then kilo means 1024, 1024. So here we're just asked, and this is just simple math here, but here we're asked if the memory size is 84 words. Well, you got to know what the word size is. We said, well, for us in here, a word size is going to be 16 bits. Well, the word size is 16 bits, and we got 884 words. How many individual zeros and ones can we store? Well, we just take the number of words that we have. We got 884 words. We multiply by, we got 16 bits per word, so we can store this many individual zeros and ones, which might seem huge to you, but for digital information, that's quite small. Now, I don't use the term kilo here, but if I put a kilobyte in there, kilobyte, you should know the difference between kilobyte and kilobit, but kilobits are hardly not used anymore. They're hardly used anymore. So when I do something on the quiz or exam, it'll be kilobytes, but know what a kilobit is. So mark this slide and study it. And if you have questions, you can ask me about it later. Here's another example down here you can look at. Okay. So this says when comparing PLC systems, you got to know the number of bytes per word. because a word is machine dependent, you got to know the number of bytes per word, and you can calculate the capacity of the memory for your PLC. So it says normally you don't need space above 128. Now this is kilobytes, so that's 1024. So you get to 2 kilobytes for a PLC. Since we're just storing the state of a switch, they're saying that 2 kilobytes is usually enough to do what you want to do. But of course, that depends on what exactly you want to do. All right, so I got like 4 minutes. I've talked about this, so I'm not going to spend too much time on this. This is your 8421 code. And so this is saying I got a 4. I got one of these, I got a 4. And I got one of these, I got a 2. So a 0, 1, 1, 0 base 2. And our number system is a 6. So you want to get used to thinking like that. So I can convert that. Here's another example. If I want to use a 12, I need an 8. I always start with the largest one first. So if I go over here, the next one over would be a 16. So I don't want to use that. I want to use an 8. So if I go 8 is the largest one, and if I subtract the 8 from there, I got 4. I keep doing that until all the value is used up. So a 1100 base 2 is a 12 in our number system, in base 10. And in this next slide, I show you the divide by 2. I use the number 47. So this is what I showed you on the board. So you can just kind of review this. Now, guys, I'm probably going to run out of time. I think I'll probably go about 5 minutes over. So if you have another class and you can't stick around, go ahead and sign off. But please make sure you go back, go to the past lecture link at the bottom of the homepage, and watch the tail end of this lecture, because there's 2 new things I got to talk about that I didn't mention on the board. Okay? And that is this. How do you deal with negative numbers? Let me go back to the board. Well, let me show you this first. So the problem is that if in a computer, if all we can store are zeros and ones, then what if I have a signed number like a -3 or a +5? There's no way to store this sign inside of the machine, because all you can put inside of a register is a 1 or a 0. So if you had a negative number, how would you handle that in digital? And it turns out there's 3 ways to handle negative numbers. So the first one is used a lot. It's called a sign bit. So that's used a lot. I think the next one is called a ones complement. That's not used a whole lot. But the twos complement is used a lot. So the sign bit and the twos complement are used quite often. So the sign bit's pretty easy. It's pretty easy. So like here, now normally, if you go by what I said before, normally the leftmost bit of each of these numbers would be your most significant bit. Well, that's not true if you have a sign bit. But you got to know if you have a sign bit or not. You can't just walk into a room and look at some digital numbers on the board and know if you have a sign bit. I got to tell you, hey, this number, this binary number uses a sign bit. If it uses a sign bit, then it acts like this. If the leftmost bit is a 0, that represents a positive number. If the leftmost bit is a 1, that represents a negative number. And that means the LS, the most significant bit, is the next one over. So all of these numbers right here, since they are zeros, that's the positive sign. And then the actual magnitude of the number is right here. So I got a 101 in our 8421 code. That's a 4, and a 1, that's a 5. So this says that 0 out front says I got a positive, and then the actual magnitude of the number says it's a 5. And down here, notice here, I got a 1 there, so that represents that negative sign right there. And then the magnitude, that 101, is a 5. So one way to show negative numbers and positive numbers in a digital device is to use what we call a sign bit. Another way to do it is something called the ones complement. Now the ones complement is pretty simple. all you got to do is, let's say we start with this number. To take the ones complement of it, all you got to do is flip the bits. So I got a 1, 1, 1, 0, 1. Where every place you see a 1, replace it with a 0. Every place you see a 0, replace it with a 1. So if I take the ones complement of this, I change all those ones to zeros, and I change that 0 to that 1. And now this number right here represents the ones complement of this. Okay, so you should know how to take the ones complement. To take the ones complement, you just flip the bits. Now we'll use this later on. Don't worry about what we're going to do with it. I just want you to know how to do it. So the ones complement, and then there's a twos complement. There's a twos complement. How can we tell the difference? I have to tell you the difference. I have to tell you, if you just walked into a room, if you just walked into the room and you just saw this, you wouldn't know anything. I have to tell you, just like I have to tell you if you're using a sign bit, I got to tell you, hey, that's the ones complement, or hey, that's the twos complement. You can't tell by just looking at it. Now, the machine that's using this, it knows what it's using. It knows if it's using the sign bit, if it's using the ones complement, or if it's using the twos complement. It knows what it's using. But as a human, you don't. If you just walk into the room, I have to tell you, hey, this is the ones complement. Hey, this is a sign bit or whatever. That's a good question. So ones complement is easy. And I'm going to finish up by talking about the twos complement. Now, if you look on YouTube, they're going to tell you to take the twos complement, you take the ones complement, and you add one. If you want to go look at YouTube, go ahead. A really simple way is this. What you do is, given a number, given a binary number, you keep all the digits the same up to and including the first one. So all of these stay the same. Up to and including the first one, you leave those alone. Everything after that, you take the ones complement of. So we left these alone, and then everything over here, we flipped those. We took the ones complement of it. Okay? So it says here that the twos complement is the most common, and it by far is. But let me go to the camera real quick. I know you guys got to go, but let's just take a second. I want to make sure, because we're going to really use the twos complement. So all I'm saying is, if you give it a number like this, like 1010, and I say, all right, take the twos complement of that, up to and including the first one, I leave it the same. I just write a 1 and a 0, and then everything after the first one, I take the ones complement of it. I flip the bits. So I got a 0 there, that becomes a 1. I got a 1 there, that becomes a 0. So if you just walked into the room and see that on the board, you would not know that this is the twos complement of that. I got to tell you. But the machine that's doing this knows that it's using the twos complement, because that's all it's going to use. You design the machine, it doesn't use either or. It's either going to use, when it does math, it's going to either use ones complement, it's going to use twos complement, or it's going to use a sign bit. So it's designed to just handle that particular way of doing things. And here, the twos complement is what's important for us. Now, guys, I'm sorry, I got to go. I got a 2 o'clock appointment, and I'm already late. So normally I can stay after and take questions, but if you have a question, please write it down, and either tomorrow I can link up with you through a video, or Wednesday after class. I don't have anything after class. Write your question down, and I'll be happy to go over it. But between now and then, just look at these PowerPoints, and if something comes up, let me know. And sorry I got to rush away like this. So, guys, have a great rest of the day. I'll talk to you on Wednesday.